Good afternoon, everyone, and welcome to the second set of second seminar on data science for for society. Today, we are really blessed to have Ernest to come speak to us. Sorry, just make sure you are muted, I think, at the moment. Okay, I will, sorry. At the moment, yeah. Ernest will be giving our second talk. He's from Sunbird.ai in Uganda. He used to be a Makerere, he used to be a Google AI in Accra. And yeah, we're looking forward to a great conversation about Kampala and actually doing data science in Kampala. So Ernest, you can take it away. And just for noting for everybody as normal, all of our sessions are recorded and we try to make as much of this accessible to people who can't make this. This is our first afternoon session. We typically used to only have morning one, so we have a mix between a morning session and afternoon session. So Ernest, yeah, you can take it away. You're muted, just FYI. Yep, you can unmute yourself now.
Great. So thanks a lot. Can you see my screen?
Yes. Yeah.
Okay. Just a second. All right. Yeah. So I'll talk about. So yeah. Thanks for having me, because it's good to be here, and good to see you again, and good to see that this group is actually going strong. I think we need more groups like this. So thanks for inviting me. I'll give a talk on some work we're doing at Sunbird.ai, which is on environmental sensing broadly. But the particular project I'll talk about will be environmental urban noise prediction for Kampala City. And here Kampala City is an example of sort of a developing country city. And there are several members of Sunbird online, so in case there's something that, so this is joint work, so a lot of them have done portions of this work, so I think I'll reference them if the questions become too hectic. All right, so what's the broader context? So the broader context is that we're trying to, at Sunbird, we're really trying to do practical AI solutions for social good. And the biggest social good currently, sort of the SDGs, these goals. And environmental sensing, especially for noise, targets the 3rd and the 11th SDGs. So we're trying to contribute towards that effort. So how does noise pollution come about? So there's been a spurt of rapid urbanization, particularly for developing country cities. This, for example, is Kampala City at night. So at night lights, tend to give you a good proxy for development sometimes. But there's rapid development. There's been rapid development, and with rapid development comes a lot of noise, unfortunately. So what is this environmental noise pollution? So the World Health Organization defines that as generally noises from sources, with the exception of workplace noise. So this is environmental noise. That's how it's described. And normally it's very, it's the same as sound, but noise tends to be unwanted sound. So there's a lot of dependency on the listener and the context. So if you look at the documentation from World Health Organization, actually, noise the biggest nuisance in noise tends to be traffic noise, because that one, almost with urbanization, that one increases. So you may not, you may not get other types of noises increasing at the same rate. So that's one thing. The second thing that the World Health Organization sort of talks about noise is that one of the mitigants, one of the ways to mitigate noise pollution is through education. So I'll just take the next 2 or 3 slides just explaining a bit about noise, why noise is a problem. So how do they quantify this environmental noise? So normally it's quantified with exposure. How much exposure do people, a population, have to environmental noise? And there's an associated risk with negative physiological and psychological health outcomes. So this has been documented by several experts in several studies. And so this limited knowledge, unfortunately, there's limited knowledge in the idea of noise sources, in regulation, in how much exposure the population is gets towards noise. And even, and particularly in developing world cities like Kampala, this is even a greater risk, because the planning is not well done. So you get noise being propagated by different sort of effects of urbanization. So in Europe, at least where you have some data, it shows that 1.6 million health years are lost to noise. And this is only specific to road traffic noise. So if you add the other types of noise, you can see that there is a huge health burden due to noise, environmental noise particularly. All right, so how is it measured? So how do we measure noise? So this noise produces changes, or it's a result of changes in atmospheric pressure. So when the pressure in the atmosphere changes rapidly, or there's fluctuation, these waves cause sound, which is noise. And so the amount of fluctuations is normally called the sound pressure. So pressure of sound in the atmospheric pressure causes vibrations, or caused by vibrations has this pressure, which is called sound pressure. So this is how it's measured in pascals. So the human range of sound pressure tends to be quite large. So from 0.0002 to up to 20. And so the way it's ordinarily measured with the current measurement meters and instruments is to convert that to sound pressure level, which is measured in decibels instead of pascals. And this is a log scale that makes it relatively easy to measure noise. And so you have a range from maybe 0 decibels or maybe 40 decibels, thereabouts, up to maybe 120 decibels. So these are normally the range in which the human ear can sort of pick the noise. And this noise level is, so when it's normally adjusted for the sensitivity of the ear. So the ear has different sensitivities to different frequencies of noise. And so there's a small modification when they do that, something called the air weighting filter. And then you get these things called dBAs, basically decibels, adjusted for the sensitivity of the ear. So this is how noise is measured. So noise meters, or in our case, we want to put noise sensors, we want to capture this decibel level that represents a particular noise or particular sound. All right, so what does this scale look like? So this scale looks like this, basically. So you have something from 0 decibels on the right up to about 140, 130. And the examples on the left are sort of examples from maybe some of them are slightly from out of our context. But I try to put some indicators on the right. So for example, a quiet neighborhood is around 40 decibels. So if you're in a library, that's about 40 decibels. That's the level of noise at that point. The World Health recommends, noise levels or workplace noise to be less than 55, more or less, for effective working. And then you get noises getting loud. So you have an alarm clock, relatively at 80 decibels. So if you're sleeping, this can wake you up because the noise pressure level is at that point. And you can see cars, trucks somewhere in the 70s. Normal conversation like the one we are having, moderate to quiet. So we're doing maybe about 60 decibels. And as you go higher, you see borders, which is motorcycles, then sirens. So they start increasing. And then you have a jet engine, which is really up there. So this is sort of the range of the noises that we're exposed to. So what are the negative effects of noise? So one, they're physical. So one is sleep disorders. So this is very nuanced. So sleep disorders manifest itself in the actual event of sleeping. So you may have a lot of, if there's even a slight noise, you may keep turning in your sleep. And then it also manifests in how you wake up the next day. You may wake up feeling, you haven't slept enough. So this could be effects of noise. So if anyone here is having bad sleep, then you want to think about, what is the noise level in my locality. And other physical effects are cardiovascular diseases, so mainly hypertension and heart attack due to exposed or a long exposure to noise. So these have been documented. Then more nuanced is hearing problems and hearing loss. So hearing loss is when you lose your sense of hearing. And normally you can tell this if you come from, for example, if you enter a car and someone's music or radio is really high, then they may be having hearing loss issues, that they have to raise the volume so high to listen. So any place where you have to shout to be heard, there is some element of hearing loss. Then tinnitus is basically buzzing in your if a plane takes off here and you can hear it, then that buzzing that remains in your ear is, that's what it's called, tinnitus. All right, so those are physical effects. The psychosocial effects, normal annoyance. So this has been categorized by World Health Organization as a health, a detrimental health effect, annoyance due to noise. So if people keep playing loud music, or you hear sustained noise, maybe from a construction site, is that annoyance that you get. Then landing impediments, which have also been documented. So noise is a real burden, is a real health burden. And so trying to tackle it is, for society, is really important. And unfortunately, in urban cities like ours, you rarely get any action being taken towards noise. So this is Kampala City, urbanized. If you've been to Kampala City, you know these motorcycle taxis we call borders. So these are they're almost more than the vehicles here. And if you look at the noise, the dBs they emit is really higher than cars. It's 20 times, 20 dBs higher, which is a factor of 2. So it's 100 times more noise, if you could say that. And so you get so many things with an urban city. So you have traffic, which increases. So you have traffic noise. You have sirens. So sirens are also in 110 dB. So sirens are particularly put at that dB level to allow people to hear them and clear them. Now in the time of COVID, we've had many sirens. Then you have street preachers, very common thing. Again, this rose up in time of COVID. You have street vendors, and you have all manner of noises that come from urbanization. So how is it being handled in Kampala? So we have the city authority, which is mandated to curb noise. And enforcement normally is done by mobile teams. And what do these mobile teams do? It's a team of maybe 3 or 4 people. They have a handheld sound meter, sound level meter. And so the law here, at least in Kampala or in Uganda, requires that for any prosecution to go on, you have to have a reading of the decibel level of the sound or noise at that point where the violation has taken place. And so how do these teams work? So they have a hotline, they have you send them an email and say, you know, there's a club next to my home that is all a site that is, the noise level seems unbearable. And then they'll come there with the meter and measure the noise at that time. So you can imagine it's very hard. You can call them, and if the person making a noise is wise enough, they can reduce it by the time they come, and then they can take an accurate dB level, for example. But also because the teams are so small and, you know, the city is large, you get all manner of pocket noises that people may even not know that, you know, they are facing noise pollution, but it actually could be there. But because it's not measured, because they don't call the helpline, you get you get limited understanding of noise exposure in the city. So there's limited noise mapping, in short, knowing where the noise sources are and how much noise is being generated in the city. And so at Sandbad, we set out to try and solve part of this problem. So at a high level, we want to do environmental noise mapping in the city. And noise pollution is inherently spatial. So you want to know where the noise source is, where it is, how many people in that area are affected, because noise, noise has a spatial limit. Once the noise source is here, there is a certain limit of distance, after which then the signal dissipates. So understanding what noise is being generated, the source of the noise, and the affected population that's exposed is what we want to do with this project. And so the goal is really to develop fixed and possibly mobile autonomous sensors that can capture noise pressure levels in real time throughout the city. So we want to deploy this throughout the city, and you can have an acoustic map of the city, and you can understand at different points of the day where noise is coming from, what's the source, and how many people may be affected. And so more granularly, we want to develop these models that we can deploy on these sensors, that given a noise reading, we can categorize what noise source that is, and possibly the location and duration of exposure of the population. So this is a big plan. So how did we go about it? So one part is data collection. So we want to build the models. We want to do data collection. So unfortunately, there is limited noise data. So I think one of the more popular data sets is urban sound 8K, which is 8,000 noise recordings that are sort of crowdsourced from, I think it's called freesound.org. Different people who have collected urban noises, and someone took them and created a data set. And so our goal was to target a larger data set. Can we, one, collect a larger data set of urban noise? Two, can we increase the categories? So from 10 to maybe 19. And can we try and get noises of an urban city in our context, in this case, Kampala city? And so we determined the categories with the local authorities, because we want this to be meaningful to them. And the goal was really to collect a large sample, large as possible, to train models for the autonomous sensors that we'll deploy. So we want to deploy sensors that can automatically detect noise, but we do not have the data right now. So one goal was to collect the data to build these models. And so we carried out an ambitious data collection exercise. So this is Kampala City. Kampala City has 5 divisions. And yeah, and so what we did, we we got 10 enumerators. We developed a form for collecting this data using ODK. So we surveyed several tools, and ODK seemed to work the best. And so the idea is that these people go out with a smartphone to the different divisions or regions in Kampala and record a 10-second segment of different categories of noise. And each enumerator, each data collector is allocated a quota of data to collect in each zone and for each category. So that means if someone's collecting, if you have 10 enumerators and they're collecting traffic data, so in zone 1, enumerator 1 will be told, okay, you can only collect up to maybe 400 sounds, and you have to collect them in places that are not the same, so you have to move. So the data collection also includes GPS. And so we developed the form, and this is sort of an idea of some of the collections that happen through Kampala City. As you can see, they are spread, and this is sort of high-level map. If you zoom in, then you get more finer granularity of where this data is collected. But the spatial spread of this data sort of covers the whole of Kampala, as you can see. So the little round circles with numbers are numbers of noise samples collected at that spot, at that geographical location. And the categories we settled on were these. So you have 19 categories, and these are sort of these are waveforms of the noise samples from each of these categories. And so from the waveform, you can see, you know, there's some of them are distinct enough. For example, animal, which is to the right, in the last column on the right, is distinct, quite distinct from maybe construction site. And so maybe you can build a classifier that can identify these. But things like school, fabrication workshop, other motor vehicle siren, you see that there may be some work to build a good model that can differentiate between these categories. All right, so we collected several, so we deployed these people for a little over 2 months, around 2 months. And the goal was to collect at least 2,000 samples from each of the 19 categories. And so this is sort of the data that came in. As you can see, some of them, for example, the category other, which was important to define, one for the modeling, but also two, to capture all other noises that we either the city authority is not interested in or that we have not thought about. You can see it's collected about half of the required quota, mainly because this is sort of a hard class to identify. Peculiar classes, we had some things like herbalists, which the regulator wanted. We're actually surprised that we collected data for herbalists. Then, for example, you see sirens. So sirens has almost 3,000 records there. So sirens was a bit, one was the COVID time, but also two was there was some quality issues with the enumerators. So the way they were incentivized was that they were paid they were given micropayments per recording per verified recording that they make. So by verification, I mean that it's not within the same geographical location. Without GPS reading is a bit distinct from the other recordings. And they verified that's a 10-second recording of whatever class is identified. And so for this particular class siren, there was one enumerator who had innovative ways of trying to maximize these benefits. Okay. So there were several quality issues, but one of the quality things we emphasized was weekly checks, that the data is checked as it comes in, that some of it is sampled and listened to make sure it's the right class. Yeah, and several other things that the team did. All right, so we set out, we collected almost close to 40,000 noise samples using a smartphone. The next item was to try and do some modeling with this data. So with audio data or sound data, so we have noise files. So we had to think of, okay, how do we represent the data such that you can compute over it? And generally, there are three ways you can do it. You can either work with the raw audio files, or you can do some feature extraction, or you can, well, an extended way of doing feature extraction is to analyze spectrograms as images. So we had to sort of think about those. Then we had to think about data processing. And so this is an audio file, so we had to process it up to where we get some tensor that you can compute over, that you can train a model with. And then also data ingestion pipelines and inference. The things we sort of grappled with. Okay, so what are the different sort of those three big classes of how to represent the data? One is the raw sound file. So this is a sound file, a wave file. So wave files are really, it's just an array of numbers. In this case, for example, these are maybe 2,600 numbers that are measured at that point. The noise, the sound pressure. And if you plot it, it sort of gives you this waveform. So working with the raw sound files is generally cumbersome because these are high dimensional. So you have, if you have a sampling rate of 44K, well, in our case, we had a sampling rate of 16,000, means every second you generate an array of 16,000 numbers. And so if you're to collect data for 10 seconds, as we're doing, then if you're to work with the raw files, you'll be working with a tensor, which is 160,000 numbers in it. So it becomes a bit cumbersome to work with. But there's been some work in actually doing this. And so we didn't use this. We didn't look into that. The other thing we looked at was feature extraction. So I think in physics, historically, these MFCC features have been a sort of state of the art with sound. So they are sort of handcrafted acoustic features that have over time been handcrafted, that they give you a good representation of the acoustic features of a sound wave. And it's very simple to extract these with Torch Audio or Librosa. You specify how many features. For example, in this case, that parameter MFCC will generate 40 numbers that represent extracted acoustic features from a sound file, a sound wave. And so this is straightforward. So you can increase those features. You can make them whatever. We tried this. The performance was generally low, and I think historically now with the deep neural networks, this is tending to be. These are not as useful as using deep neural networks. Okay, so the third thing we really focused on, or that we did, was extracting melt spectrograms, which are images, the frequency by time image of the sound, the noise, basically. And these present, you can look at them as images. And because you can look at them as images, you can you can use convolutional neural nets to work with them. And so this is what we basically did. So so that's one, data representation. So we went with the MEL spectrograms. So the other item was preprocessing. How do you preprocess the data? And basically we used PyTorch, and it has a module called Torch Audio, which has special routines for processing audio. But basically the steps you want to, or the steps we took was one, check if the samples, all the samples collected have the same sampling rate and the same number of channels. So our app was basically collecting mono sound, so one channeled sound, that's stereo. And we're using it was using a sampling rate of 16,000. Normally, people use a slightly higher sampling rate of 44K. We use 16K. This was the data we collected. So you want to check that all the samples have the same rate. Otherwise, when you convert them to a MEL spectrogram, you'll have different representations of the data if you've not made sure that these things are uniform. And then the second preprocessing was resizing the audio. So we wanted it to fit within 10 seconds. So the enumerators, when they went out and they were recording, traffic, a motor vehicle, they record maybe 10 seconds, 12 seconds, 18 seconds. Well, a siren, it may go off at 8 seconds, or it may go on for 15 seconds. So in order to generate the same sort of image, we could say we had to make sure that we resize all the audio files to fit within 10 seconds. And basically this is either truncating the file or adding quiet time, basically adding zeros to it. Then the third thing is, generate the spectrogram, the MEL spectrogram from the audio, and then some augmentation of the spectrogram to prevent overfitting and have the model trained better, better generalization. So what are the different types of augmentation? So Torch Audio provides two useful transforms. One is called frequency masking. So if you look at this image on the right, on the left, which is being frequency masked, so you can see the original MEL spectrogram. And then what happens with frequency masking is you take slices out, you take horizontal slices out of the image, and you replace those slices with the average of the whole spectrogram. So basically it will look like something on the left with stripes that are blank in between. And then you can also do time masking, which is basically blocking out the vertical lines, which is the image on the right. Again, the same thing, you basically take strips out and replace those strips with the average over the whole spectrogram. And this sort of works the same way you have annotations or augmentations of images, where you rotate, you crop, right. Okay, so that was the processing of the data. We prepared it, processed it. At the end, after some cleaning routines with the data, we have about 37,000 audio files that are good enough for training. We did 90% of the data for training, which is about 33,000 audio files, and a test set of about 10% of the whole data, which comes to about 4,000 audio files. And the test set was selected such that it represents the distribution in the training set is represented in the test set as well. And then really at this point, we tried some random architectures of convolutional, blocks, and some railroad activation and batch norm. So empirically, batch norm actually tends to improve the performance of when working with MEL spectrograms. So this is what we found out. And so we do some training with this one to see if there's plausible accuracy, if things can actually work at this high level. And so evaluation is mainly the standard evaluation metrics. One for class-wise performance, what is the recall precision for the different categories of noise, and then a confusion matrix for seeing what things are being confused. And then we also did manual evaluation, so listening into to some of these audio files. All right, so some quick results from some of the training. So we basically get on average 70% accuracy. So this is sort of a confusion matrix, and basically I think the interesting things for us here to see was, for example, we see that, for example, if you look at the fourth row, second column, so for motorcycle or border and car and truck, we see that these are confused, and this is expected because the motorcycles are traveling on the same road as the motor vehicles. So ideally, if someone was recording a motorcycle, it's likely they would get a background noise of a motor vehicle. So these seem plausible, which means, you know, the model was sort of learning something. So for example, car horn was being confused with car alarm. So again, those tend to be things that's a plausible confusion. And so we had some comfort that the model seemed to be doing fairly well. All right, then for the different, sorry, this should read something else, but these are the results for the different classes. And we can see here, I wanted to see which classes is it easy to identify. So for example, we see animals, is a very distinct sound that the accuracy there is quite high, and the recall as well, the F1 score. Things like a motor vehicle siren, which is a very distinct sound, we see that also accuracy is quite high. Herbalists tend to be, the model seems to get them accurately. So the things where it doesn't do well, things like motor vehicle horn, which is different from the siren. That one can't really distinguish quite well. Yeah, even the other category is a bit ambiguous. Then car or truck again is a little bit problematic. And we've seen part of the reason that this gets confused with the border motorcycle, which is also quite low. So, you know, there's some level of good performance, or at least understandable performance from these the model. All right, so basically that was it with the modeling, and the idea here, maybe I'll explain at the end what the goal was. But the idea here was, okay, given this data set, can we come up with a model and see how well it does in differentiating these audio files, and then the idea would be to transfer this to a smaller model that can fit on a sensor. All right, so the next item was sensor development, and here the goal was to build an autonomous sensor which is low cost and efficient. Sorry, there's noise in my background. Well, this is ideal for a sound noise presentation, though it was not intended, but I think you can hear it, so that's a clear demonstration. All right, so the idea, so the steps basically was to test some modules, different modules for building the sensor, and then work through different transmission or communication protocols. So how do we get data from the sensor to the server and back, and then test things like which microcontroller would be best. Then things like the microphone, and how do we measure sound pressure levels, and how do we calibrate that? How do we know that our sensor is measuring the right things? And so it has been, and my colleague Nasa, who has actually been doing this, is on for any questions with the sensor development, but it has gone through a cycle of testing different components. The first was a mega microcontroller, which didn't quite work. We had got the STM32 with a 3G, 4G SIM module that tends to work, but then you get other sort of complications. So we've sort of iterated through different types of components, different testing, building of circuitry. Several other things that come with sensor development, things like monitoring information. How do we do monitoring information of the sensors? How do we handle noise files? So this has to do also with the privacy. Are they processed at the sensor? Are they not? How do you send them to the server? These kinds of things. How do you know that the whole file has been sent? So there's several sort of issues that come in with trying to build communication and transmission pipelines. And then finally, these triggers for noise. How do you measure noise with an autonomous sensor? Do you measure at a certain threshold? When a threshold is reached, is it when you initiate measurement, or is it continuously on? And how do you make that efficient? Yeah, so we've gone through, the team has gone through, NASA and team have sort of gone through a lot of this developing boards. We're now at the stage where we're deploying, we are deploying two sensors, two version 1 sensors. So we are sort of moving on. So one key thing here was calibration. So how do we know that the sensor is measuring accurately? And so we used a Casella sound pressure level meter. So this is a standard meter that is used by the authority here in measuring noise. And so we used it to calibrate our sensor. A very convoluted process of building preamplification boards, circuits, and things like that. But this is definitely critical, that each sensor is calibrated with a state-of-the-art noise meter. All right, so this is our sort of final version 1 sensor that is being packaged and deployed this week, and the goal would be to collect some data from it, see if it works, and then from here build a more refined version 2 of the sensor. Right, so this is the end of the presentation. So there are several next steps that are going to happen. We're going to try and improve the model. We're going to collect data from the sensors. So we collect the data using mobile phones, which roughly represent the sensors. But sensors, are deployed at different heights. So we want to collect data from there with mounted sensors and see if the models still work well. And then want to, of course, build models for deployment on the sensors for edge inference. Yep, so thank you.
All right, thank you, Ernest, for that. That was very insightful. I didn't expect that. That also, it's great seeing also working with both on the side of the electronics and also on the machine learning on the other side, that almost end-to-end work that's going on in here. I just wanted to open up for questions. So if you would like to ask a question, please just raise your hand and then I'll acknowledge you and then you can ask the question to Ernest. On there, I guess a question maybe just to kick it off while people bring up questions is, especially with like, what are the, if you think about this as scaling this, the data storage, how that is going to go, are you, like, the processing, sure, that's happening on the edge devices. Do you think that can be made more efficient so that you don't need to send as much data to kind of a central space on there? I don't know, like if you have any comments that has to do with the scaling.
Yeah, so yeah, so scaling is definitely something we want to build in from the get-go. So we actually don't want to send the actual audio files to the server. One, for privacy, because these are autonomous sensors mounted. They could record people, talking. So we don't want to send that file. So we really want to process it at the sensor level and send maybe a result of that. So for scaling, that is definitely one thing we want to do. But other aspects of scaling, I think I talked about it earlier, was having mobile sensors. Can we get mobile sensors? Maybe people with mobile phones. Is there a way to have people collect noise from their localities, and somewhere we can verify or validate these recordings so that you build this acoustic map. Yeah, I think those are sort of the key aspects of scaling. Of course, the other things, like want to make the board more efficient, want to power it with solar, which is sustainable, want to make it cheap, want to integrate with the network of people who do hardware, the Jua Kali, I think they call it in Swahili. So the people who can maintain these things by maybe building enclosures, building brackets that can hang them onto walls. So create some sort of sustainable pipeline that people can benefit from this, or can build business models around it, and then the city can sort of take it up with the payments. So yeah, thanks.
Okay, thank you. As I said, if you want to ask a question, either you can put it in the chat, or I guess in this case, you can unmute. We still have some time, and then ask, just say who you are and then ask your question. I guess I also don't know if it's a Friday thing in the afternoon.
People don't want to add to the noise.
Yeah, I guess in another part, sorry, now it's maybe coming down to if I'm saying this is coming connected maybe to the electronics, and this betrays more my background is in electrical engineering, and it's something I still I dabble in privately, not in research. But then if you are going to have kind of edge devices like this, or you're going to it is cheap enough, I think, to have more poly mobile phones that you can put in specific places, and you just need to then focus on the software. But if you do go for customized hardware, was there any thoughts of adding other sensors outside the noise on there? Because I can see things like air quality sensors being something that could be useful over a period on that part. So as you answer that one, or your colleague does, I'll also just read the question that's on here, and then I'll read the question to you after the answer.
Yeah, yeah. So we definitely this was sort of in the plan to build an environmental sensing box, a toolbox with multiple sensors. So not only noise, but we also wanted to hinge on the air quality network that already has sensors deployed, and see whether we can add some of these noise sensors with that in the same box for places where it makes sense. So for example, air quality monitoring, you can have that mounted on a moving motorcycle, but maybe that's not the right place to add a sensor. But for those which are deployed on buildings, then you can also add, for example, noise, but also noise. Yeah, so basically it's the idea is to really have a box where we can have multiple sensors, which makes it more flexible than a smartphone.
This might have been taken care of, but there's a question from Tapelo on here, who's actually here in South Africa. He's saying he read that, like, working with sound, it's better to obviously convert, sorry, not obviously, to convert your data into an image and then process the image instead. So he's asking about your experiences with that. Was it better to work an image versus working with features extracted from the sound?
Yeah, so I think it really depends. So if you have very limited sound data, then maybe extracting features may be more useful to extract, those acoustic features, because these have been refined over historically by I think their colleagues in physics, and so they actually extract these very deliberate features. But if with more data, then I think image data tends to work best. Though of course now there's a shift towards raw. Using actual raw files, then you cut out all this baggage of preprocessing. I think DeepMind has something on, I think it's called Deep Wave or DeepNet, where they're using actual raw audio files. So that's also a direction people are taking to cut out. Basically, the way we went for, to just using images direct with deep neural networks instead of going through the process of extracting features. So there may be pros and cons in these things. I think it's a fertile area of research.
All right, thank you. Are there any more questions? I know there's been a couple of comments, people just saying great presentation. So I'm back on campus, so there is some background noise. There's a lot of construction that's going on. Okay, if at the moment there's no questions, for me, like, this was a great example of ways to use machine learning in better understanding our environment. I think also oh, sorry, there is a question there from Abdullahi. Oh, there's a question about how will you monitor the sensors themselves? Is it possible that they might actually get damaged or taken away?
Yeah, I think this would be a good point to ask my colleague Nasa if he's still there to answer that. Nasa?
Yep, I'm there. Hello, everyone. My name is Nasa. So how we are monitoring all these sensors, we have set up an online platform where all these sensors keep streaming this data. So we get to understand what the battery condition looks like, their connection signal strength, and the current dBA level at that particular time. Yeah, and if they would be damaged or taken away. So I think that one is about the installation, how we are going to position them such that they are within the community, but then still not easily reachable. That would be one way that we are going to work around it. Yeah, and again, I don't know what they would want to do with them when they take them away, because perhaps they will not be able to communicate with any other system unless they are reprogrammed. Thank you.
Thank you, Nessa. Just to close it off, I wanted to thank Sunbird.ai, it seems here, which is both Ernest and Nessa, for coming in and giving this talk. As I was about to say, this is a great example of looking at a problem that sometimes comes up in urbanization, given the places that we stay. It's very much like, looking at a problem within our society and then looking through a scientific lens on how one can try to deal with that problem. And that's what, like, especially as you're saying, we're doing data science in society. It's one, not forcing methods on problems, but looking at problems and then trying to identify that, like, if there's a good fit there, or some of the technologies that we are looking at as scientists and trying to resolve. Just before everybody came into the talk, one also for Sunbird.ai is also being a startup and the challenges that come with that in building such technology. So good luck to them. I do hope to visit Uganda soon, and it would be great to also connect with Sunbird and also some of the people at, I think there's some people here from Makerere I've seen on the, sorry, on the Zoom. Enjoy your weekend, and we look forward to also seeing you at our next seminar, which should be, I think, on the 23rd of September. We're going to have 3-week breaks in between now, the different ones. And yeah, thanks, Ernest, again.